Thank you everyone for coming for this final day of the data-driven decision processes bootcamp. So compared to other programs, we're going to do something slightly special today. And instead of going over some new topics, we are going to sort of go over the legacy of David Blackwell. But before I go into this, since we're all doing data-driven decision processes, here's a data-driven decision processes question for all of y'all. So when does anyone have a prediction as to when someone will write the last paper on these topics on data-driven decision processes?
Last paper.
The last paper.
When the world explodes?
Nobody, okay, so I'm glad to see nobody's confident enough to say in a year I'm working on it. So there actually is, as long as you're frequent as there is a data-driven way of talking about this, it's sometimes called the Copenhagen Principle. And the idea is we're not special. The field exists in some time. We sort of sample it at a random time. So in some sense, if you want to predict when the last paper on this topic is going to be written, a good predictor is actually looking at when sort of the first paper on this topic was written, and then basically multiplying by 1/40 and by 40 to get a 99% confidence interval. Now, I'm sure many of you don't completely agree with this. That's because y'all are all secretly Bayesian, but you won't admit it. But that sort of raises the question of when was the first paper in this area written, this area that we are defining in this bootcamp. And as I posited to you before, I actually think it's the following. So this is a paper back in 1949 called Bayes and Minimax Solutions of Sequential Decision-Making Problems, which really completely lays down exactly all the things that we were talking about in a very proto version, but at least like we could have taken that topic and named our semester after that, and none of you would have blinked. And so sort of going from that, it's been around 80 years since that was written, multiply and divide by 40. The last paper is going to be written within either 2 years or 320 years. If it's within 2 years, please credit the Simons Institute for doing work while you were here. So we're going to celebrate the second author of this paper, but let me sort of show you a quick video of the first author of the paper talking about writing this. So this is Canaro. So he said in the year 4849, let me try and.
And one of the things I worked on in the summer of 48 was with Gershik and with David Blackwell, who subsequently Howard University, who subsequently went to, unfortunately, at Berkeley. We tried to get him here, but that was a big disappointment. Yeah, we can't win them all. The outstanding mind.
An outstanding mind. So this is Canaro sort of talking about one of the other greats in this field, talking about this gentleman, David Blackwell, and how in a talk which was supposed to be about Canaro's life and the history of Stanford, he couldn't sort of help himself and stop for a few seconds and just comment upon how great this person was. And so that's what we are here to talk about. And I'm sure many of you must be asking, well, okay, why a whole day dedicated to David Blackwell, and why now? And I'll try to give you sort of 3 answers to this question. So the first one, which is perhaps the truthful answer, is that we started planning this program. So along with Theodoros Dikouris, Shuchi Chawla, and Shipra Agarwal, we started planning this around 2020. And as we were sort of thinking about all the topics we wanted to cover, and then of course looking at the news, and in some sense in both just in terms of the intellectual contributions, but also in terms of just the societal impact and the role that David Blackwell plays as a role model, we just couldn't help thinking about him. Everything we were doing, it sort of seemed to tie back to David Blackwell. And so when we finally wrote down the proposal, we decided that a large part of it should be centered around the legacy of this gentleman. But I'm sure many of you will be like, yeah, okay, that makes sense. But surely there's some special anniversary or something that this commemorates. Now, for those of you who are, I guess, ancient Sumerian or coders, or like if you believe in the hexadecimal system, it has been 12 years since David Blackwell left us. And so that seems like a special occasion. But unfortunately, or fortunately, most of you are conditioned by the Hindu Arabic numerals. And so you would rather find something that this is the 10th anniversary of. And it just so turns out that this is the 10th anniversary of David Blackwell being awarded I think it's the National Medal of Science. He was awarded it posthumously in 2012. And so before I hand over to Ricky, I'm going to show you a quick video that was produced on the occasion just to explain the legacy of David Blackwell. And in the process of the video, you will see him giving a lecture. I think this is quite long back in the 60s, where he's talking about tossing a coin and trying to predict or just getting a sequence of zeros and ones and trying to predict what the sequence is. And he'll draw this very mysterious looking diagram where he draws an X and Y axis. And he says, let's look at the number of ones and the number of times we've got it correct, and then do this very strange thing in between. And I'm hoping our next speaker, Ricky, can illuminate a little bit about what exactly he's doing there. So let's quickly do this video, and then I'll hand it over to Ricky.
What were the odds this Illinois child would become one of the world's great mathematicians? David Blackwell was game to try.
I was always pretty good at mathematics. I don't know that I had favorite subjects. I studied whatever you were told to study. Did it as well as I could, but I looked forward to recess. I was a good student, mind you.
Such a good student that by age 22, he had earned a PhD from the University of Illinois.
There's a lot of luck in things. The man that I chose as my thesis advisor was far and away the best possible choice I could have made. His field, probability theory, turned out to have a lot of appeal for me. It turned out that I like to think that way.
Blackwell wanted to teach mathematics, and he wanted to serve at historically Black colleges and universities.
I got a list of all the Black colleges from some almanac. There were 105 of them. I wrote 105 letters. I actually accepted the first offer that I received as soon as I got it. And my really serious mathematical work started at Howard. At Howard, the intellectual atmosphere was just different.
Suppose that every day a machine produces a number, either 0 or 1.
In the mid-50s, Blackwell joined and soon after headed the University of California, Berkeley's newly created statistics department. Over the years, Blackwell continued to expand mathematics by introducing game theory, decision theory, and information theory into the field.
Let's suppose in particular that we knew that all these xn's were greater than or equal to a half.
David Blackwell, the first African-American elected to the National Academy of Sciences, dedicated to assisting disadvantaged students in the US and Africa.
First, the advice I would give to young people generally is try everything and keep looking until you find something that you like.
What's his thesis advisor? What charisma.
Since someone said what charisma, that's a perfect segue to introduce our next speaker.
Thank you.
Can everyone hear me? Okay. So I thought what I would do, so even though the title of my talk is about the David Blackwell's Approachability Theorem, I would first say a little bit about David Blackwell, but more generally about sort of the academic milieu in which David Blackwell was born into. I'll get to why I will do that in a moment. And then I realized from talking with Sid that given my time, I may not get to the technical parts. but I hope you won't mind. Okay? So I think one often reads the story of David Blackwell or interprets it as it's the triumph of genius over racism. And while that's a possible interpretation, I want to describe sort of the wider environment in which David Blackwell was born into, and in some sense come to a more pessimistic conclusion, which is it's right time, right place. And so the picture that I chose for David Blackwell is one that appeared in, some of you may have seen this, many years ago, Time Life, two companies that no longer exist, but at one time were quite prominent, published a sequence of 5 volumes devoted to the various sciences with profiles of mathematicians and scientists in them. One of the volumes is devoted to mathematics, and David Blackwell is one of the people that they profiled. I think this came out in the mid-60s. And this is the picture that they picked. It's a younger David Blackwell sitting on a table. There's chalk in his right hand. It was one of the things you will notice if you read many of the oral interviews of David Blackwell. He is always jumping up and going to the board to explain things. Okay. So what was the environment into which David Blackwell entered? So I have here a list of the first 10 or so PhDs in mathematics awarded to African Americans. I want to caution you that you will find lists like this on Wikipedia and other places. They should be read with some care. Some of them will amalgamate PhDs in mathematics with doctorates in the teaching of mathematics. So I have removed those from this list. And those lists are sometimes incomplete. There are some names that don't appear. But over here, I hope you can see Elbert Frank Cox is the first African-American to have received a PhD in mathematics. And I've cut off the list here for a variety of reasons. 1, running out of space. 2, running out of time. And 3, after 1943, there is a change. There is a change that's visible in society. And I will get to that in a moment. Okay. You will see here is David Blackwell. And so what can we say about these individuals? Well, for example, she's the first African-American female to have received a PhD in mathematics. What was the profile of these individuals? Mostly they were getting PhDs for a combination of reasons. 1, they were primarily involved in teaching, and getting a PhD was a way to advance within the administrative ranks. What was special about these individuals was that they chose PhDs in mathematics rather than PhDs in education. So the typical profile would be get an undergraduate degree, perhaps start in high school, then get a master's degree, wait a couple of years, and then go on to get a PhD. An extreme version of this is Woodard. Woodard was a dean of arts and sciences at Howard University. In his 40s, he decides to go back and get a PhD in mathematics from the University of Pennsylvania, studying under the same, so he decides to go back to get a PhD in mathematics from the University of Pennsylvania, returns to Howard as a regular faculty member. Right? So that's it. He gives up all other administrative positions. Okay, so what's special then? So what makes Blackwell stand out in a variety of ways? Well, the most obvious is that David Blackwell in this list is among the first to go undergraduate, master's, PhD. Okay? With all of these others, there are gaps, with one exception, William Schifflin Claytor. Okay? Let me say a little something about these others. Pierce is an interesting individual. He played football for the University of Atlanta, and his goal at the time was to be a football coach. In his first appointment, he is asked, can you teach mathematics? And he says, yes. So he's assigned to teach mathematics and apparently discovers a love for it, and eventually goes on to get a PhD in mathematics, but stays primarily as an educator. Reuben Roosevelt McDaniel. One of the things to keep in mind at this stage, in this time period, is that schools for African Americans were different from schools for whites. For example, in the South, 5 months of schooling was mandated for African Americans, 6 months for whites. And the required amount of schooling was 5 versus, I think, 7 years. Those numbers keep changing as you move around the South. Son of a farmer, he has a falling out with his father because he recommends to his father that the father do crop rotation. The father thinks the son a bit arrogant. There is a fight. The son is sent to live with his aunt in Washington, D.C. By this time, he's finished his 5 years of mandated schooling, and he has a job as a postman. One of the places where he delivers mail to is the office of the Navy, where he meets the future President Roosevelt. Now, the middle name does not come from that. There is some ambiguity about how it's spelt. On some documents, the E is this E is missing. On other documents, it's present. But Roosevelt encourages him to go on to high school at night. During the day, he finds a night job for him. He eventually goes on to get a PhD, but once again, primarily the focus is education. Okay, so 3 individuals that I now want to talk about: Claytor, Blackwell, and Wilkins. Okay, undergraduate, PhD, and then on to research. Okay. Claytor. He comes to Howard, gets an undergraduate and a master's degree, goes on to get a PhD. First job is at a small university in Virginia, where he is the mentor for Catherine, what is her name from Hidden Figures? I apologize.
Which one is she in Hidden Figures?
So I just remember her first name, Kathleen, and I've forgotten the last name because Johnson? Yes, Johnson. Sorry, and Johnson was not her maiden name, which is why I'm confused. Okay. Paper from his dissertation is published in the Annals of Mathematics. It's a generalization of the Kuratowski theorem to surfaces other than planes. His advisor, John Klein, was also the advisor of Dudley Woodard, who was Claytor's mentor at Howard. Klein writes that this is probably the best thesis he's ever supervised, and attempts to get Claytor into the Institute for Advanced Studies in Princeton. Now, at that time, the Institute for Advanced Studies was housed in the same building as the mathematics department at Princeton. The mathematics department at Princeton was firmly desegregated, and Claytor did not succeed in getting a fellowship at the Institute for that reason. He's struggling at this minor institution in Virginia to get research done because of the teaching loads. So eventually, his advisor wangles something for him at Michigan, initially unpaid. Okay. Subsequently, he wins a Rosenwald Fellowship. I'll explain why the Rosenwald Fellowships are important in a moment, which gives him funding for about a year. But it is clear from correspondence at the time that the insecurity of his position is cutting into his ability to do serious mathematics. He ends up hanging around in Michigan for about 2 or 3 years, and without any kind of academic appointment. He has some kind of unofficial academic appointment. He is not permitted to attend the seminars at the mathematics department at the University of Michigan. Eventually, the Institute for Advanced Studies gets its own building. They ask him to join them. And at this point, he is completely frustrated and writes back, "I have no intention of being a guinea pig." He joins the army. World War II has started, where he teaches artillery. And when the war finishes, he is hired at Howard, where he spends the rest of his professional career primarily focused on, only focused on teaching. Correspondence from his wife suggests that the frustration with racial barriers completely turned him off from the mathematical community. Okay? Now we come to David Harrell Blackwell. So Blackwell graduates from Illinois. He also gets a Rosenwald Fellowship. The Rosenwald Fellowship was money from the Rosenwald Foundation. This is Julius Rosenwald of Sears Roebuck fame. Julian Bond has pointed out that in some sense, much of the African-American intellectual aristocracy were funded at the early stages with Rosenwald money. So this is why, so Plato was identified as a talented individual very early on, received the Rosenwald funding, but the barriers were for him too much. And so he ended up in some sense exiting research mathematics. Okay? David Blackwell also gets a Rosenwald Fellowship. The institute is now desegregated. He goes on to the Institute for Advanced Studies and spends a year or two there. Okay, first job is at a university in Louisiana. He's there for a year, then to Clark University in Atlanta for a year, and then Howard University, where he spends about 10 to 12 years. Okay? So openings in majority institutions are typically not available to graduates at this time. If you look at where I cut off the dates, what you will notice is that you will then start to see that some of the individuals who receive PhDs, their first academic positions are at majority institutions rather than at HBCUs, historically Black colleges and universities. Okay? Now, another one I want to point out is that we sometimes overlook is Jesse Ernest Wilkins. So there's an interesting difference between the two. Blackwell was born in Centralia, Illinois, to a relatively prosperous family. Father was, although as described as a railroad worker, was actually a manager, and mother was a school teacher. Jesse Ernst Wilkins's father was a cabinet member in the Eisenhower administration and received his PhD from the University of Chicago at the age of 19. He also received a Rosenwald Fellowship and went to the Institute for Advanced Studies. Only job he got was at the Tuskegee Institute, again, historic and HBCU. He went there a year and then afterwards was asked by Wigner to join him in the Manhattan Project. Okay? Wilkins eventually left academic mathematics for a while. Why is that? He had a far more promising career as a nuclear engineer. He went on to earn 2 degrees in engineering from New York University and was a prime example of the technocrat that arose from the end of World War II. He had an expertise in nuclear power, and he ended up becoming the second African-American to be inducted to the National Academy of Engineering. Okay. What is interesting is that Blackwell and Wilkins met only once. When Blackwell was head of the mathematics department at Howard, he attempted to hire Wilkins. Wilkins came for the interview. At that time, he was what we would now call a chief technology officer at the American Optical Company. And instead of accepting the offer, Wilkins, in fact, recruits one of the junior faculty members that Blackwell has just hired, whose name often is missing from these lists of PhDs in African Americans who received PhDs in mathematics, hires him into the American Optical Company. So that was their only contact. Many years later, after Wilkins had retired basically from industry and government work, he returned to Howard as head of the department and set up their PhD program. Okay? So what I want to sort of this is why, now, why do I want to say this is a story about right time, right place? Just look at these three individuals. So both of them, all three of them showed great promise early on, except the outcome for Claytor was dramatically different. Okay? Now, what was interesting, I think, about these two, not just the fact that the institute was desegregated, it is also that these two were involved in areas that were soon to become big. For Wilkins, it was nuclear power, nuclear energy. What about David Blackwell? Well, David Blackwell was in Washington, D.C. He himself describes the mathematical atmosphere at Howard as moribund, probably not his word, but my interpretation of his description. So how did he continue to be mathematically active? And the reason is because towards the tail end of World War II, many mathematicians were going to Washington to consult. Arrow, Gershik was the chief statistician at the Department of Agriculture. Danzig was coming regularly, and David Blackwell was working with them. So this would be the early days of an area that we might now call the mathematics of decision-making. David Blackwell was there at the start. In fact, he had met some of these people much earlier in his career when he was at the Institute for Advanced Studies. And in fact, even earlier when he was an undergraduate at Illinois, one of his contemporaries was Abraham Chance, one of the early pioneers of linear programming. Okay? So this is what I mean by right time, right place. Those connections enabled him to spend the summers at the Rand Institute in California. And so this is why my interpretation is it's less about genius triumphing over racism, because I look at the fate of William Claytor, and more about right time, right place. Right? Okay.
Maybe the power of collaboration.
Say again?
Maybe the power of collaboration.
It's the power of, right. So it's a number of things coming together. And in the oral interviews of David Blackwell, he is always very careful to emphasize that he learns a lot from other people. Right?
We all do.
We all do, right? And so David Blackwell, in some sense, was lucky enough to benefit from that, and you know, William Claytor not. Okay. Anyway, so that's sort of the background. Later today, you will hear sort of more personal reflections on David Blackwell, but I think providing some background of the general milieu is useful. Okay. Now, based on the interviews that I've read, these are Blackwell's 3 favorite papers. This offers an alternative theory of probability as a competitor to the Kolmogorov interpretation. Blackwell himself complains that nobody has really taken this up. All right. Here's the second, and you'll notice I have 3 papers. They're all related to approachability. The reason why I put them together is the following. This is essentially a lemma that is used here. This, I think, is what motivated David Blackwell to produce this. So this, if you like, is the first published application of approachability. Blackwell would call this the vector minimax theorem, okay? Which is why I bundle these 3 together. Okay. Third favorite paper is the one on merging of opinions. So let me tell you very quickly what this is about. I have a prior distribution over some state space. You have a prior distribution over the same state space. Then things are drawn from the state space. We update our priors a la Bayes. Is it the case that our posteriors will converge because we are looking at the same information? Okay, the Blackwell-Dubin's theorem says, as long as my prior is absolutely continuous with respect to yours, in other words, we don't disagree in the following sense. You assign measure 0 to something that I assign positive measure to. Okay. we will eventually converge, and that notion of convergence is called merging. Okay. Okay. Now, the reason why I mention this will come a little later on in the talk. I'd like to talk about the approachability theorem and tell you a little bit about its connections to sort of more current research that many of you will be familiar with. Yes.
Is that kind of like the Allman theorem?
So the Allman theorem is about, no, so in the Allman theorem, it is you and me exchanging information, right? So here there is no information exchange. It is simply we are observing draws from the same urn.
Related to misspecified priors.
No. So the no, it's the so with misspecified okay. So with misspecified priors, it's that you don't have the correct prior distribution. In this case, both of us, there is no statement about that. We simply have two different priors, and the only question is under what conditions would we eventually agree on the distribution of the state space. And the condition is that, look, there has to be some kind of agreement in our priors to begin with, which is this absolute continuity condition. Okay. Let me describe now the approachability theorem, and I'm going to describe it without any interpretation in terms of games. I want to describe it simply as some property of sequences. And so here is one version. I'm going to give you a sequence of vectors from a bounded set. I'm going to keep track of the average of the vectors. Every new vector in the sequence that I pick must have this property. Now, if you think of these vectors as being numbers, then notice what this condition is saying. If the current average is positive, the new number that I give you must be negative. If the current average is negative, the new number I give you must be positive. In other words, the new number that I give you must be on the other side, where the origin represents the dividing line of the average. What's the conclusion? That the average has to converge to 0. Now, I think if you think about numbers, you say, yeah, that has to be true. Okay? And so here I replace number by vector, and this, of course, must be dot product. So therefore, yeah, it's the other side. Okay. Let's generalize a little bit. Okay. I will give you a sequence of bounded vectors. I will give you a convex set T. Again, I keep track of the average. And now I want to keep track of the closest point on the convex set to the average. My new vector, xn plus 1. Okay, so let's see, let me draw a picture here. Here is T, here is the average. That's this pi t of an. And then what is this condition saying? It's saying that my new vector must be on opposite this. Opposite means what? It must be something like this, on the other side of this tangent hyperplane. If this is always true, then eventually my averages have to converge to something in the set T. Right? Again, if you think about it, yeah, that just seems absolutely has to be right. Right? Next variation, everything as before, except now, before this dot product was deterministically negative, I've added expectation. Okay? So now all I'm telling you is that this new vector is generated from some distribution. The only property of the distribution is that the expectation of this dot product is less than or equal to 0. Now you say to yourself, huh, that's the only difference. If these xn's are IID, then of course this conclusion has to be true. Okay? Where's the subtlety? I've not said that these have to be IID. Okay? So the remarkable feature is I only need that expectation to hold. I don't need these xn's to be independent draws. Now, how do you get this? You get this using, in Blackwell's paper, from the lemma here, from this lemma here, which is essentially a version of semi-martingale convergence, right? So you need something stronger than the standard law of large numbers. Okay, so this is the approachability theorem, purely mathematically, no interpretation whatsoever. Yes?
Quick question. The expectation is not even conditioned on the past?
Not even conditioned on the past.
Oh, it's just the...
Just the expectation at that instant. Okay, so here is the interpretation that Blackwell provides, and this is why he calls it a generalization of von Neumann's minimax theorem. I have a two-player game, and again, my two players are called row and column. They repeatedly choose a strategy, so column chooses a column, row chooses a row, but the outcome of the game is not a single number, as it is in the standard zero-sum game setup. The outcome of the game is a vector. Okay. What I keep track of is the average vector produced. There is a target set which is convex. What makes this a game is I want to know if R has a strategy that forces the average towards the target set. And the approachability theorem basically says a convex set T is approachable if and only if every tangent hyperplane of the target set is approachable. Okay. So mathematically, it boils down to, do I have a mixed strategy at every stage that guarantees this condition? If I do, then I just invoke this result. So applying the theorem means simply making sure you can do this at each stage. Okay. Okay. Now, the theorem has been generalized in every way I think you can imagine. And so just for your edification, I think I've captured every possible thing that you could play with. Blackwell's version has finite actions for column and row. You can generalize that to compact action spaces. Approachability is in terms of the Euclidean distance between the average and the target set. You can replace it with other norms. Blackwell was looking at the simple average of the outcomes. You can do various kinds of weighted averages. Blackwell had finite dimensional vectors, infinite dimensions. You can relax convex target set to a closed target set. Blackwell was relying on randomizations. You can then ask how well can you do if you restrict yourselves to deterministic strategies. In Blackwell, both sides can observe everything. They see the whole game. You can relax that to some kind of partial observability. And if there's any variation I've ignored, please tell me right now.
I missed on the row column player. What were the actions of the row?
Row is simply choosing a row of a matrix, and column is choosing a column of the matrix, but each entry of the matrix is a vector.
Like, what's it relate to in this picture?
Okay, so in this picture, when I choose a row, you choose a column, the outcome is a vector. And we do this each period. And then we look at the average of the outcomes, which would be the average of the vectors. The average of those vectors is this. I just realized one other. It's discrete time. There's a generalization to continuous time. Yeah.
There's one thing with the convex target set to closed target set. I can't get almost.
You can't get almost. As Blackwell would say. Yeah. Okay. Now, why on earth is this theorem useful? And this is where I'm going to explain the little snippet that you showed from Blackwell. So it turned out that a year after Blackwell published his vector minimax theorem, James Hannan published his paper on Bayes minimax regret. Right? The Hannan paper proves a theorem that has been proved many, many times afterwards in different areas. Right? So in computer science, it's known as the expert's theorem. In information theory, it's called universal compression. In game theory, there's a connection with fictitious play and learning in zero-sum games. And Blackwell pointed out that Hannan's theorem was a special case of his vector minimax theorem. And he wrote up a little note showing how you would do the argument. I have only seen a version of it from around the early 2000s. So this cannot have been the original note. But if you look in the appendix of Luce and Rafer's book, Games and Decisions, they actually describe the Hannan theorem, and they point out that it's a consequence of the approachability theorem of David Blackwell. And so I simply want to show you how you would use it in this context, and then you will see why approachability is useful. So I'm going to ask you to predict the next element of an infinite sequence of zeros and ones, and I'm going to measure your performance by the fraction of incorrect guesses after n periods. Okay. And so I want to keep track of this, which is the fraction of ones, hn. 1 minus hn is the fraction of zeros. And what Blackwell is going to convince you of is that we have a strategy with the following property. If you follow it, the fraction of incorrect guesses is smaller than the fraction of incorrect guesses if you predict 1 all the time or you predict 0 all the time, plus an error term that's going to 0 as n goes to infinity. In the context of the language of experts, you have 2 experts. One expert, I know it seems an exaggeration, only predicts 1, and the other expert only predicts 0. And this says that by combining their predictions, in some sense, you can do better than both of them. Okay, so how do you do this? Well, here is the idea. L02 is going to be the error at time t if you predict 0. L1t is the error at time t if you predict 1. So I'm keeping track of your mistakes from predicting 1 and your mistakes from predicting 0. Now, the outcome from predicting 0 at time t is going to be represented as a vector. The vector has 2 components. And the outcome from predicting 1 at time t is going to be represented by this vector. So here is the game. I'm row. I can choose 0 or 1. Your column. You can choose 0 or 1. What's the payoff? The payoff is not a number, it's a vector. Now, L0 is the error from predicting 0. L superscript 1 is the error from predicting 1.
And in that, with the first coordinate being 0, sorry, in the last line, the first coordinate being 0 means.
Oh, you're asking what's the interpretation? So the answer is, I simply want to, so rather than present aggregate error, I want to separate out the nature of the errors into 2 components. That's it, okay? Now, so now what Blackwell is going to ask is, let the target set be the negative orthot. Can I push the average of these over a number of rounds into the negative orthot? Okay? Now notice, if I succeed, then that would mean that both of these components must be the average of them over time, must be less than or equal to 0. Okay? In other words, I must be doing better than predicting all 1s or predicting all 0s. Okay? So let WT be the probability of predicting 0 at time t. What would the average of those vectors be? It would be this. Right? So this counts up the mistakes when you predict 0. and you predict 1. So the way to think about this is the regret you would feel. So you predicted 0, and then you ask, gosh, what if I had predicted 1 instead? Target set is the non-positive orthant. And now it's enough to check whether the negative orthant is approachable. So you just check that hyperplane condition. And if it is, you're done. I'll skip the algebra because if you can approach the negative orthant, you're done. The existence of such a scheme is given. Not only do you have existence, the proof itself gives you an algorithm. Okay, so this is the basic way in which the approachability theorem is used. You look at your online decision problem, you reformulate it as a vector zero-sum game, you identify an appropriate target set, and then you check a hyperplane condition to see if you can approach any tangent hyperplane to your target set. Okay? Now, does this give you the best possible algorithm in all circumstances? Not necessarily, but it's an off-the-shelf algorithm to get what you want to get. Okay. Now, so Hanan, I think, called this property no regret, or people afterwards have called this no regret. There, and in an early paper, Dean Foster and I gave this a formal name, no external regret, in the sense that here is Hanan's theorem, which is this is your loss from choosing action I at time n. So you can have more than 2 actions. The losses don't have to be 0, 1. Any bounded number will do. And there exists a randomized rule so that your average loss is less than the smallest average loss from your best strategy in hindsight. There is another notion called internal regret, which goes roughly like this. I look at all the times that I played action I, and I ask, what if I had played action J instead? And I do that for all possible pairs. And I want all of those differences to be going to 0, meaning I don't want any regret, any sort of lack of consistency in the choice of my actions. When Dean Foster and I proved this, it was stronger than standard no regret. I'll get to the rest of the story, I hope, in time. And you can prove again using David Blackwell's approachability theorem that such no internal regret strategies exist. All right. Okay, so the picture you should have in mind is approachability implies Hanan no regret. Approachability implies no internal regret. No internal regret implies Hanan's no regret. Okay. All of this from approachability. And now let me tie this back to merging with something that seems at first glance very different. Instead of choosing actions, I'm going to ask you to make probability forecasts of a binary event. So you're looking at an infinite sequence. I want you to tell me the probability of the next entry in the sequence being a 1. You're free to announce different P's in different periods. How should I measure the accuracy of your forecast? Okay. Now, of course, the problem here is if I say there's a 50% chance of rain and it rains, that's not a mistake. Okay, so here is one way that you might think about measuring the accuracy of my forecast. Look at the average of all of my forecasts and compare that with the average of the ones. If those are close together, then presumably I'm telling you something informative. A little reflection will show, wait, that's a little fishy. Here is a potential outcome. Here are forecasts. By this measure, I'm looking good. But of course, I seem to have missed the trees for the forest. So you can say, we understand what's going on here. You know, looking at the aggregate sequence, that's losing information. Why don't we be a little more refined? Why don't we break up the sequence into 2 subsequences, for example, even periods and odd periods, and then impose the same requirement on the even periods as you do on the odd periods? Well, here's another example that says, wait, even that's going to be fishy. I simply predict 0.5, but again, I seem to be missing completely the pattern in the data. So then you might say, oh, wait, we know what to do now. You'd like to break up the data into different subsequences. So let's do the breaking up via an algorithm. The algorithm is called the checking rule. So how can I break up the subsequence? Well, the decision to include any period in a subsequence, we can allow it to depend on the history of the outcomes and the forecast to date. So you give me a collection of checking rules, basically a collection of subsequences. My goal is to make probability predictions so that on each subsequence, the average of my forecasts is equal to the average of the ones. Okay? So to pass a checking rule means that on the relevant subsequences, the average of your P's should be close to the average of your ones. A very particular case of this is called naive calibration, where the checking rule is as follows. I look at all subsequences where you announced, let's say, a 10% chance of seeing a 1. The fraction of ones should be 10%. I look at all subsequences where you announced a 23% chance of seeing a 1. The fraction of ones should be 23%. So this is the condition I would want to hold for all possible choices of P that are announced sufficiently frequently. Why? Well, if you announced a probability 0.27 only once, nothing really I can do with that. Okay, well, given a checking rule, is there a forecasting algorithm that will pass it for all possible realizations of the data via Blackwell approachability? The answer is yes. Given a finite collection of checking rules, is there a forecasting procedure that will pass all of the checking rules simultaneously? By Blackwell's approachability theorem, yes. What about any countable collection? In other words, any Turing computable algorithm for producing checking rules? By the appropriate generalization of the approachability theorem, the answer is yes. Okay. Now, before you get too excited and think, wait, we've solved the problem of forecasting, there's a negative interpretation of this, which I'll get to in a moment. What about all checking rules? This, it turns out, is related to Blackwell's third favorite paper, merging, which is if you had a forecasting procedure that passed all possible checking rules, whatever probability distribution that you are announcing must merge in the sense of Blackwell and Dubin's with the true underlying probability distribution. And so what this analysis highlights is the importance of how you measure accuracy. Calibration, the way I described it, is a backward guarantee, meaning I go into the future, I look back, and I tell you I look good. Merging is a forward guarantee. Merging says I go into the future at some point. Beyond that point, I'm going to guarantee you that you're going to look good. Much stronger requirement, but much more demanding to meet. Okay, I'm almost at the end of my time here. So approachability implies Hanan, no regret, implies no internal regret, implies calibration. In the last couple of years, people have closed the loop. You can start with calibration. Any algorithm that passes any countable collection of checking rules can be an algorithm that can be used to prove Blackwell's approachability theorem, and can be used to prove no internal regret, can be used to prove no regret. So the circle now is completely closed. In some sense, all of these mathematically are the same object, okay? But they have very different interpretations. So Blackwell was originally interested in generalizing the minimax theorem. And when we get to this particular way of thinking about things, it's a question about how can I tell whether you indeed know something? And this is the negative interpretation. I know nothing at all about the weather, but I can make probability predictions that will look very reasonable. Okay? This should make you suspicious. Right? Okay, and I think let me end here unless there are questions. Go ahead. Go.
Can a checking rule be all subsequences? Like
any countable collection of subsequences.
So a checking rule can...
So the checking rule can be a function of the history of the outcomes and the history of the forecasts. And that's obtained from a generalization of the approachability theorem to infinite dimensions.
Could you just quickly give the reference for the closing the loop? Okay. So the closing the loop is the result of independent work by different individuals. But if you are looking for a nice survey of all of these together, there is a survey paper by Vianney Perchet, Perchet, or you can send me an email. I think it appeared in the Journal of Dynamics and Control in 2014, I think. And it has all the proofs and has all the formal statements of all of the results. And so one-stop shop. Okay, well, thanks very much.
I guess we've all noticed we're going to shift the schedule back 20 minutes. So we'll shift the morning back 20 minutes and we'll catch up after lunch. So you have your full time. You would not want to cut you off. Okay, let's see. Are the slides not quite up yet? Okay, perfect. So I don't use it in your text. So we have we go from Blackwell approachability now to a very nice application of it.
Thank you very much, Adam. Okay, so hello everyone. Thank you very much for attending the talk. I think, and thank you, Rakesh, for giving a